estaré colgando el enunciado de los requisitos para el ensayo que nos toca hacer para la clase esta semana, porque la idea es que el primer ensayo lo tengamos antes de que salgamos a la semana de receso, ¿bueno? Para que oficialmente pues, puedan ustedes tener el 30% para su curso. ¿Listo? Bueno, entonces es un placer para mí presentarles al doctor Bastien Grosso.
Doctor.
Doctor no, todavía, pero ya casi. Bastien hizo su pregrado en el ETH de Lausanne, en Suiza, y actualmente es estudiante de doctorado en física en ETH, en Zürich, y pertenece al grupo de la profesora Nicola Spaldi, que pues, es una líder en el campo de cálculos teóricos en sistemas de materia condensada y sistemas fuertemente correlacionados. Y es un placer para mí tenerlo acá. Bastien tiene un español perfecto, pero nos va a hablar en inglés, porque es complicado hablar en español estas cosas del trabajo. Entonces nos va a hablar sobre sus sistemas multiferroicos y espero que disfruten muchísimo su presentación. Bastien tiene vínculos con Colombia supremamente chéveres y fuertes, y ustedes están invitados a hablar con él lo que ustedes quieran preguntarle al final de la presentación, ¿vale? Entonces un aplauso.
Gracias. Bueno, muchas gracias, pero sí voy a hablar en inglés porque es más fácil para mí, para la investigación y la ciencia, pero creo que me pueden hacer preguntas en español más tarde. Entonces, muchas gracias, Paola, y gracias a ustedes de ser aquí. And now I'll switch to English. So I'm happy to be here and present you my work. It's actually not going to be a lot of my work. I will more try to explain you what is the concept of multiferroics in different forms, why it's interesting, and I hope I'll convince you. So just before starting, just a brief motivation. In general, for modern technology, there are different functionalities that one wants to use based on physics. For example, in order to store information, one can use ferromagnets, where you have spin up and spin down, for example. That would correspond to a 1 or a 0 byte in a computer. You can also have sensors, which can use ferroelastics, which means that if you apply a stress in your material, there will be a strain response from the material. And there are also sensors based on ferroelectrics, which are materials that have a polarization that one can switch by applying an electric field. And it's great, these properties, but it's even better if one can find materials that can combine few of them together. And it's actually existing for example, transducers, where you can have a change of polarization that will also change the shape of your material and would allow you to detect what happens. Another interesting part would be to have something that would be ferromagnetic and ferroelectric. And multiferroics are based or interested in those kind of materials that can bring together these two properties. So with that, I'll just like to give you the outline of the talk. So first I'll tell you what are multiferroics material and why they're interesting. I'll then show you how one can engineer multiferroics material. And then I'll talk about a particular multiferroic material that is bismuth ferrite. You'll see why it's so special. And after that, I'll go to another application, that is how can one engineer layer by growing different types of material together, multiferroics. And the last part will be my own research, as I will present you later. So let's start with the first part. What are multiferroics? So I talked about magnetism and ferroelectricity. Let me start by ferromagnetism. I'm sure you're familiar with this, but just as a quick reminder, one defined a macroscopic magnetization in a material, or call a material a ferromagnet, if at high temperature it is magnetically disordered, and by lowering the temperature you order the spins in your system, or the magnetic moments. You can order them in a ferromagnetic way, all in the same direction, antiferromagnetic, half in one direction, half in the opposite direction, or we can have what is called ferrimagnetic, which would be similar to this, but with a different amplitude for one direction and the other one. So this one will result in net magnetization of your system. It is, the ferromagnet is characterized by this hysteresis loop, where you have here the applied external magnetic field, and here the magnetization of your material. And when you apply a magnetic field, you are inducing magnetization, but then when you remove the field, it doesn't go to zero, but it stays with the spontaneous intrinsic magnetic field. I will just present you here what is a perovskite structure, because it will be important for what will follow. So perovskite structure is a type of arrangement of the atoms in a material or in a crystal. It is composed or labeled by A, B, O3, where A and B are metal ions, and O stands for oxygen. And it has, in the perfectly cubic unit cell, this type of shape, where you have a metallic ion in the A site, here in the corner. In the center of the cube, you have a B site. It's called B site. It's also another metal ions. And then on each face, you have an oxygen. And you can define the lattice parameter of your crystal by this relation, which is the ionic diameter of the central atom plus the two oxygen. Or you can also define as this way, which would correspond to the diagonal of your cube. And those arrangement of atoms, as you will see, are very important for multiferroics. So I presented magnetism. Let me go to ferroelectricity. It is actually very similar to ferromagnetism, or it's analogous, because you can replace magnetization by polarization. You can replace magnetic field that you apply by electric field, and the magnetic flux by the electric displacement. And you also find this type of hysteresis, where when you apply an electric field, you produce polarization in your material, and when you remove the field, you don't go to zero. And you can apply the opposite field and switch to the opposite direction. They also have some of the ferroelectric material, this type of structure, and the ferroelectricity can have two origins. First origin can be by displacing this central atom out of the center of the cube, and this will create a dipole, which will induce the polarization. So that's one type of way to engineer or to induce ferroelectricity. Another way is not to do it in the B site, but on the A site in the corner. And this is actually done by having electrons that are not bounded. They are not participating in the bond with another atom, and they stay free around the atom. And here you can see what would be the density, for example, of the electronic density, which would correspond to have these electrons. And this will also create a distortion and polarization, or in the opposite direction here. So now, ferroelectricity, ferromagnetism, let's go to multiferroism. So here you can recognize the three pictures I showed in the first slide. Let me, from now on, forget about this part and just concentrate about these two parts. So a material combining at least two ferroic properties, so polarization, magnetism, or ferroelasticity, in the same phase is called a multiferroic. And each of the ferroic order, for example, polarization, can be switched by the conjugate field. So for example, polarization, you can switch it by applying an electric field. Magnetization, you can switch it by applying a magnetic field. But there is also a cross interaction. So for example, in some cases, you could influence the polarization by applying an magnetic field, or the other way around, by applying an electric field, you could change the magnetization. Why they are interesting? For two reasons, or many reasons, but those could be two possible applications. So imagine that in the same phase of your material, meaning at the same temperature, in the same conditions, you have a material that has polarization and magnetization. If polarization and magnetization are not coupled, meaning that you cannot influence the polarization by the magnetic field or the other way around, then you could have four states in your system. You could have spin up, polarization up, spin down, polarization down, or the other combinations. So that would result in a higher density storage device. If they are coupled, meaning that you can influence polarization by magnetic field or the other way around, then the interest of this is that you could imagine that you could switch the magnetic moment of your system, not by applying a magnetic field that is very energetically costly, but by applying an electric field. And that's why these are interesting materials. Then the next question that is an honest question is, why then we don't have multiferroics memory already in your smartphone or in your computer? For answering this question, let me go to what are the reasons why a material is multiferroic. So we said that multiferroism is when you have these two ferric orders at the same phase. So that means that your material should be ferromagnetic and ferroelectric. So let's see now the origin of these two properties. If we consider symmetry, just meaning the positions of your atom in the crystal, you can actually find out of 122 symmetric possible systems, only 13 would allow to have simultaneously a spontaneous polarization and a spontaneous magnetization. So that's already not a lot of combinations that are possible. Then to have a ferroelectric material, you should have a material that is insulating, because if it's a metal, then you would have charges floating around and you could not have a net polarization in the material. On the other hand, ferromagnets, they are often metallics, so they are metals, which is a problem for this to go together. But further than that, if one look at the origin of the magnetic order, actually to have a magnetic net magnetization in your material, you need to have partially occupied d or f orbitals, meaning that you can, if you have two spins, for example, in your two electrons in your orbitals, they will be in the same direction. But if you now fill all the possibilities with up and down, then they will cancel out and you have no net magnetization. On the other hand, for ferroelectricity, most of the ferroelectric materials in the Perovskite structure that I showed here have empty d orbitals, which is contradictory with this. And more than that, if you have partially occupied orbitals in the d or f orbitals, then the structure tends to be centrosymmetric, which means non-polar. So for example, this would be a centrosymmetric structure, and this would be a non-centrosymmetric, which will have the polarization. So you see that from these points, it's not so easy to find material that would combine both together. And that's why it's not so easy to find this material and have application from them. So with that, let's see now how one can use this Perovskite structure in order to build these multiferroic materials. So we saw that you have ferroelectricity, that it can be on the A side or on the B side, and we saw that there is also the magnetization or the magnetism that has magnetic order that has to be also in your structure, in your material. So maybe the first easy way would be to think, okay, I have two types of atoms. Why don't I choose one to have my magnetic property and one to have my ferroelectric property? So that's what we can now explore with these two combinations. Let's say one would be magnetic and the other ferroelectric, or the other way around. And I will show you two examples of material that correspond to each of these cases. So the first one is called europium titanate, which is magnetic and ferroelectric, but under certain condition. Actually, it is antiferromagnetic with the magnetic ordering in plane, so you can see here. So this is the crystal structure, and here you have the A site, that is the magnetic one. I'm sorry, it just shifted by half of the unit cell, that's why you don't see in the corner this big atom, so don't be confused from that. So this material is antiferromagnet in plane, which means, and it's a G-type antiferromagnet. It means that if you consider one atom that has a net magnetization, the neighbor, in-plane neighbor will have the opposite direction, and the out-of-plane neighbor will also have the opposite direction. So that means that overall, it's not magnetic, because everything is canceling out. And more than this, it has the structure, the symmetry of the structure, it doesn't matter the label here, is centrosymmetric, which means non-polar. But I told you it was an example of multiferroic. Actually, it is, because it becomes ferromagnetic instead of antiferromagnetic, and ferroelectric, but under large strain. So that means if you compress your material, then it will have these properties. The opposite example is bismuth ferrite, which I will spend some time on it. So bismuth ferrite is a ferroelectric material and also magnetic. It is ferroelectric below 1100 Kelvin, which means, and it has a large polarization, sorry. This is a large value if you're not used to polarization values. And it is antiferromagnetic G-type, so the same as the other one. The neighbor in plane and out of plane have opposite spin direction. And with this two temperature, what you can notice is that it's actually combining these properties at room temperature, because you can go below this temperature, you are room temperature, and you would have the two properties. And that's why it's the most studied multiferroic material, because it's the only one that is multiferroic at room temperature. And it has this crystal structure with the polarization that would be along this diagonal here, and the spins that would have like one type of spin here and the opposite direction for this one. So let me now talk a little bit more about bismuth ferrite and tell you what are the properties and applications. So before that, let me just go with a quick reminder on what is the super exchange interaction. So imagine that you have a crystal like this, and you have two atoms that are in blue that are with a magnetic moment. And they are bonded by this oxygen atom that doesn't have any net magnetization. Let's assume now that this atom, it's iron 3+, which means that in the d orbital there are 5 electrons. And as you know from quantum mechanics or chemistry, in order to put your 5 electrons in these 5 shells, you have to put them all in the same direction to fulfill Hund's rule. If you do that, so that would be this one, for example, it would have net magnetization, let's say up. Now we said that this one has a bond with the oxygen atom in the middle. As all these spin are up, and according to the exclusion principle, then in the bond you have to get an opposite spin coming from the oxygen. So the oxygen would have, this is the orbital of the oxygen, it would have a spin down in that part. Having this, it's only one spin remaining, and it has then to be up. And this constrains the other atom here to be all down, because then the up is already taken, so it can only share a down spin, or down spin. And this means that due to this, the two atoms here will have opposite spins. And that's why super exchange favors anti-parallel alignments of the spin, in this case between the iron atoms. Another interaction I will tell you about is called Jaloshinsky-Moriya interaction. So we saw that super exchange, just what we saw before, favors antiferromagnetic order, so opposite spins. Then there is something called spin-orbit coupling, and a simple way to see it would be the interaction between a particle spin and its own motion. And this coupling favors usually perpendicular spin, so 90 degrees. But when you combine both together, you have this interaction called Jaloshinsky-Moriya, which can be expressed in that way. And I will just decompose it. So imagine that you have, that's what we had before. So now we are breaking a symmetry, and we don't have here a 180 degrees bond, but we have an angle between the bond. So the Jaloshinsky-Moriya interaction can be defined by the cross product between the two spins, so the spin here and the spin here, with the scalar product with this vector that breaks the symmetry. And this vector is actually the vector of the bond here and here. And it's also the vector product. So when you take that together, to minimize this, it will actually favor to have this canting, meaning it doesn't stay like this, perfectly parallel, but there is a small angle between the perfectly parallel spin due to the symmetry broken here. And from that, you can see that when you have deformation in your lattice, it can also induce a magnetization. Because when you had the two spins that were perfectly opposite direction here, you have no net magnetization. But here, you have a net moment in both in the same direction, so it will result in a small magnetic moment of your system. So from this, let's go now back to bismuth ferrite. And I told you that it was G-type, meaning opposite spin in plane and out of plane. And I showed you that this was the structure. So from this, due to the anisotropy, you can imagine two possibilities for having the direction of your spins. First would be you have here the 1-1-1 direction, so the diagonal here. So you could have a spin down here and a spin up here, parallel to this 1-1-1 direction. Another possibility would be to have the spins in the plane perpendicular to this 1-1-1 direction, with, for example, in that direction one spin and the opposite direction the other spin. And using density functional theory calculations, which are numeric solutions of Schrödinger equation for materials, one can compute these two configurations and compare the energy and find that this is the lowest energy one between these two configurations, meaning that the spins should be perpendicular in the plane here. So let's say we start here. So this result is also numerical, so from this Schrödinger equation solved numerically. And we said that here you have the 1-1-1 direction, and we said that the spins should be perpendicular to that direction in the plane. So let's start from this. We can run the calculation, and we will get this final result. And you can see that in the final result, they are not perfectly aligned like here, but they canted a bit, from actually about 1 degree. And this results in having a weak ferromagnetism of about 0.1 mu Bohr per unit cell. So it's a tiny amount, but still it's a small net magnetization. Why this is important? Because I told you that for applications for multiferroics, one would look for ferromagnetic and ferroelectric system to switch or to have the couple between them. And I told you that bismuth ferrite was ferroelectric, so that's very good, but antiferromagnetic. But now we see that it has a small canting that would result in a small net magnetization, which would be good for application. So let's go a little bit further. And if we had this, then we would have a ferroelectric and ferromagnetic system. But actually, there is another phenomena that happens, is that if you imagine that you have your material here and you repeat it in all directions, in black here, you see what would be the antiferromagnetic direction, meaning you would have one spin going in that direction and the other one in the opposite direction. But what happens in that material is that not all of this repetition will stay exactly like this. They will rotate and do something like this, which is called a spin spiral. And that means that overall, there is no net magnetization. So even if we get a weak ferromagnetism, it's actually cancelled in the material due to this, which has a large periodicity of about 64 nanometers. So with that, I'll just show you now two applications with bismuth ferrite, just trying to motivate you that it's still cool material, even if it's not ferromagnetic. So one possibility was done in this study, where bismuth ferrite was grown on top of a substrate. So for the substrate, they have two types of material, which you can see here. And each material has a different spacing between the atoms. And usually what happens is that the substrate is the one that will impose the distance between the atoms in your material. So by having this substrate with this lattice parameters, so distance between the atoms, you can see that it's actually different from the one of bismuth ferrite. And when one grows bismuth ferrite on top of these two materials, you can see that this applies strain. And these are numerical calculations, but are actually reproducing experimental results. And what you can see from here is that when you apply strain, you are actually, let's consider this one, you are actually increasing the energy, because that's not what the material would like to be, the spacing. But what happens is that when you compress in plane, it relaxes out of plane. And we saw that the out of plane is also linked to the polarization. So what happens here is that when you compress this material until these large values of strain, then the polarization increases. And it goes from about 90 to 100 microcoulomb per centimeter square. So about 50% more than it was initially. And this shows that by changing the in-plane, you can also induce more ferroelectricity or a larger polarization. Let me go to now a more fun example, a little bit out of material science, but it has been shown that bismuth ferrite can be used for cleaning water. So imagine that you have an organic pollutant in your water, and you have bismuth ferrite, or a part of this material, in your solution. What is known is what is here. So generally, what people do to clean water from this organic pollutant is by applying light here to the material. This material will absorb the light, and this energy will create electron-hole pairs that will migrate to the surface of the material. By doing that, they will start oxidative or reductive reaction, and this will result in degradation of the pollutant. But what they observed is that if they put here bismuth ferrite, they put bismuth ferrite in that solution, and they stimulate mechanically, so by applying sound waves. By doing this, it implies a strain in bismuth ferrite. And you saw that strain, just what we saw before, will have polarization enhanced. And actually, by this strain, it goes a larger electric field inside the material, which results in improving the performance of this cleaning. So that's just to show you that it's still interesting material. So just a partial summary. I told you that there are multiferroics material that combine these different properties. They're interesting because one can have an increased storage density or a lower energy consumption memory. I told you that there are two prototype examples. Eurobium titanate, which is antiferromagnetic and ferroelectric when one applies strains. I told you that there is also bismuth ferrite, which is antiferromagnetic and ferroelectric, but multiferroic at room temperatures. And what I told you is that actually bismuth ferrite is antiferromagnetic with a weak magnetism, but this is not enough to have a net magnetization. So still, this is not a ferromagnetic ferroelectric system. And without being ferromagnetic and ferroelectric, it's difficult to sell this material for applications. So let me show you now another way to engineer multiferroic materials. In general, due to the growth techniques, one can create materials by choosing which atoms go in the A site or in the B site. You can apply strain in your material, as we saw, and that would result in enhancing polarization, for example. But there is more. Imagine that you have a substrate, which implies strain, and you grow on top one type of material, and then you alternate with another type of material. By doing that, there are many interactions that will happen here. For example, you can have at the interface mismatch between the atoms, so the bond length, or you can have chemical problems, or you can have electrostatic effects. I'll come back to this later, and many things. So that means that you have a lot of things you can try to control in order to push your material to go to the direction that you want. And this was actually done, and it was the first time that people showed that one can engineer a multiferroic material not by changing A and B atoms, but by stacking together two types of material. To do that, they considered lutetium ferrite and lutetium iron 204. And this material is ferromagnetic, meaning antiferromagnetic, but with different amplitudes. So it has a net magnetization, but it's not ferroelectric. This material is antiferromagnetic, but ferroelectric. And the idea is that they are not so far away. You can see from the chemical formula that they look similar. And the idea is to stack them together and see if one can transform this material that has a magnetization to also have ferroelectricity. So that was done by starting the growth with the lutetium ferrite and then introducing iron oxygen in a controlled way. And by doing so, you see that you have here your ferromagnetic system, here the ferroelectric system, and by combining them together in that way, so that means 9 unit cells of this one for 1 unit cell of that one, you get this material where you can see that you have here these distortions, and these distortions are responsible of the polarization or the ferroelectricity in your material. And for this particular system, they observed that it was indeed magnetically ordered, so ferromagnetic, and it has also a polarization, small value, but still it's a proof of concept that you can engineer multiferroics by also this technique. So with that, I'll go to the last part of my talk, which is what I am involved in. And so far I told you that we were looking for ferroelectric, ferromagnetic material. But let me now ask a different question. Can we not care about ferroelectric, ferromagnetic, but look for other interesting properties coming from this material by controlling what happens in these heterostructures? With that, I'd like to acknowledge first the collaborators. So Nicola Spalding, which is my supervisor, and the experiment were led by Julia Mundi, which is a professor in the US, and Colin Hikes, and all the collaborators. They did the experimental part, and we did the theoretical part. So in general, if you have this heterostructure, so meaning you have a substrate, one type of material, another type, and again the first type. Let's now assume that the green one here is a ferroelectric material, which means that you have alignments of dipoles like this, which will result, if this is non-ferroelectric, non-polar, to a discontinuity here at the interface. So what happens is that this alignment of dipoles will result at this interface of net charges, plus here and minus here. And this will create depolarization, but it's also a problem because it brings a discontinuity of this material. This is due to the Gauss law. So Gauss law says that the divergence of the electric displacement field, which is defined here, is the sum of electric field and polarization, has to be equivalent to the amount of free charges that you have in your system. But if this is an insulator, then you don't have free charges. The free charges are zero, and that equation means that the D has to be constant. So to be constant, it means that this part should be equal to minus this part. And this is what happens in your heterostructure. You have the polarization in one direction and the depolarizing field or electric field in the other direction. It's called depolarizing field because it cancels the polarization in the system in order to remove charges here. And usually people want to fight against this depolarizing field because, as I told you before, we want to have ferroelectric materials and to be able to switch them by applying electric field. But let's go in a different direction here. So imagine that you have a non-polar material, a polar material, and again a non-polar material, as I showed you in the heterostructure just before. If the non-polar material has a good screening, imagine it's a perfect metal, it can move charges around and come in the interface and screen the charges, and this polar material will stay polar and stay happy. Now imagine that you have something that is a bad screening or an insulator. Then in order to minimize the charges here, a way that the material finds is to split into domains like this. Remember that this might be, for example, one unit cell or many unit cells in that direction. So that's what the material prefers. But because of this discontinuity, it has now to make a balance between staying as it wanted to be and screen charges. And a way to do that is to split into these domains, because you will have a part that stays in the bulk or in the ground state, and here again, but with the opposite direction, and you don't pay anything at the interface, but you have something here that happens now. Another possibility, instead of doing this, is to rotate the polarization from out of plane to in plane, because the material will be large in plane and thin out of plane. So that means that here it doesn't really matter if you have the charges accumulated, because they will be so far away that it's not a problem. And by doing so, you also remove the charges at the interface. But another possibility is to have a phase transition, so that it means that the crystal structure will change from this polar arrangement to another non-polar arrangement. And in that way, you would have something non-polar, and something non-polar, and no discontinuity. So that's the question that we want to ask here. Can we stabilize a non-polar phase instead of splitting into domains or having this rotation? Why we want that? Because so far I told you that ferroelectrics are interesting for application. But actually, non-polar material could also be interesting. And more than this, there are many ferroelectric materials, but there are not many antiferroelectric materials. What do I mean by antiferroelectric? So ferroelectric would be all the dipoles in the same orientation. Antiferroelectric would be half and half in the opposite direction. It will result in no net polarization, but the interest is that if you see here this hysteresis loop, when one applies the electric field, you induce polarization. And if your material is a normal ferroelectric material, then the energy that you will lose will be proportionate to the surface here, but the energy that you can store will be proportional to this purple surface. For an antiferroelectric, it would be in this shape. So it will be a linear response first, and then you will recover a ferroelectric behavior like here. But when you remove the field, you go back to 0. But what is interesting is that you can store more energy here in that case. And that's why antiferroelectric materials are interesting. And there are not so many. And the problem also is that they are usually composed of lead, which is bad for environment, and people are trying to get rid of them. So that's the motivation of having this non-polar phase instead of the polar one. So let's go back to our system with this cartoon. So imagine that you have a material that is in the ground state polar. So there is a net polarization, and it is surrounded by a material that doesn't screen well, an insulator, for example. So in that case, you will have the internal energy of this would be the lowest because it's the ground state, but there is an electrostatic energy to pay here due to the discontinuity at the interface. And this energy is proportional to the squared of the polarization. In the other case, if we assume that we have now a phase transition to a non-polar material, or non-polar phase, sorry, but the same material, that means that the internal energy would be higher here because it's not the ground state, but there would be no electrostatic energy to pay. So it could be that one can find a balance between that would favor this case over this case. And a good candidate is bismuth ferrite. I told you it was an interesting material. Why it is interesting? Because we saw that it has a large polarization. And having a large polarization, it means that it has a large electrostatic cost. But more than that, it also has a rich phase space, meaning that you can imagine that you have the atoms arranged in different ways, and each way would be labeled by one space group here. But what is interesting is that these are also numerical results. If you consider this size of unit cell, you can actually find all these possibilities and the energy here, so that's the ground state, this is the 0 energy, and then you can find different other phases that are not so far away from the ground state. So that gives a good hope that one can find a higher energy phase but not too high, and that would be better than having this large electrostatic cost. And that was actually experimentally achieved by Giulia Mondi and her collaborators, where they considered superlattices of bismuth ferrite surrounded by lanthanum bismuth ferrite, so meaning that they replace a percentage of the bismuth by lanthanum, and they did that for a concentration of around 40% of lanthanum and 60% of bismuth. And by doing that, for this concentration, this material is not polar, and this one in the ground state is polar. So you would expect that this could go to a non-polar phase. And that's actually what happens. They observed that building this heterostructure, the bismuth ferrite layer go to an antipolar, meaning meaning some atoms moving in one direction, some atoms in the opposite direction, which would result in no net polarization. So let's have a look on what they observed experimentally on this layer of bismuth ferrite surrounded by this. So now we'll zoom on this layer. And this is what you can see here. So these are STM images, sorry for the S, which allow you to see the positions of your atoms. So imagine that you grow your crystal like this, and what they do is that they observe the alignment of atom in that direction, for example. So the material grows in that direction, and here you are seeing a projection of everything that is behind what you see here. And what you can see here is in bright white the bismuth atom, and here you might be able to distinguish the iron atoms, and you don't see the oxygen because they are too small. So that's what they observed. They observed this type of structure, which consists actually in having here in red, I colored the bismuth to help you. You would have here two that would move down and two that would move up, and continuing that way. And this is actually close to another material that is antiferroelectric, or this opposite direction of polarization. They also observed these two structures. So what you see here is actually the same. distortion, but just with the rotation. So here we are seeing the 100 axis is here, and here we have the 110. So basically 45 degrees rotation to visualize. And what they see here is that here you can notice that you have a displacement in plane, diagonal, and the opposite diagonal, and it alternates. And when you rotate this, you see 2 up, 2 down, flat, 2 down, 2 up, and it continues the repetition. So from these images, it is clear that there is an antipolar displacement in each of the direction that we are considering here. So now let's go to the theory side and see how we can identify this structure. So to do that, we can consider different arrangement of atoms and solve them numerically, so compute the energy and see which are stable, which are unstable, and which are low energy. So the first distortion that I showed you was the 2 up, 2 down. And I just colored here the unit cell to help you, and this is what we computed theoretically. And you see, maybe it's not easy to see, but it's actually here, these two are moving up, these two are moving down. Now if I rotate this structure so we're seeing something like this, and now I will put it vertical, this is what you get. And you can see here that you have 2 up, 2 down, flat, 2 down, 2 up, flat, 2 up, 2 down, and so on, which correspond to the other distortion I showed you. This means that this phase or this arrangement of atoms correspond to the one that was experimentally observed. And it also means that these antipolar displacements are also verified theoretically. And the way that we were sure that this was the correct structure was by taking these structures and simulating these images. And you see that there is a perfect match. The symmetry of this is called PNMA. Doesn't make so much importance here. Just know that it's a non-polar phase or a centrosymmetric structure. It is still G-type, so that means that the spins are out of plane and in plane in opposite directions. And let's call this one PNMA antiferroelectric for a reason that will become clear. So now we identified the structure, but we need to understand why this is the structure that appears in the experiment and not the ground state, which would be just polar. So the first way to check is to think about the strain. You saw that we said that when you apply strain, you can change some properties. So let's consider here different structures and fix the in-plane lattice to the substrate that was experimentally grown and put the zero energy for the lowest energy one, which is still R3C. And you can see that this is still the lowest energy according to the strain, but there is this phase that is the lowest one above this polar ground state. But that means that the strain is not explaining why this is not happening, but this is happening. But let's go now to an electrostatic consideration, which was the initial motivation of of this study. And for that, we will build a model. So this is theoretical, it's not experimental. We can build a model and assume that for this model, the energy is the sum of an electrostatic contribution and an internal energy, meaning what are the interactions between the atoms and how this is favorable or not. And we consider now the R3C phase, which is the polar ground state, with the lowest non-polar phase, which is the one we identified. And again, we assume that we have non-polar material surrounding bismuth ferrite, and the same here. So for the polar case, you will have polar material, non-polar, discontinuity, accumulation of charges as we saw before. If the material goes to a non-polar phase, everything is non-polar, no problem. In terms of energy, that means that now we can say that here in this case there is the internal energy and there is this electrostatic energy also. In that case, there is only the internal energy. And now, as this is not favorable, we assume that we don't break into domains because that was not what was experimentally observed. And we assume that there is a mechanism that the material will try to use in order to decrease this discontinuity. And this mechanism is an overestimation because there are mechanisms that would be cheaper. But to overestimate it, we assume that the material will try to screen these charges by creating electron-hole pairs above the band gap and moving them around in the material to go to the surface to screen here. So that would be the screening cost, part of this electrostatic. So the electrostatic is a positive energy, and this screening cost tries to lower the energy. In the non-polar case, there is no screening because nothing has to be screened. So now we can compute this too. I will not show you what are the equations, and it's not so relevant for this. But what we can show is that if we compute now this energy for the polar case and this energy for the non-polar case as a function of the thickness of this bismuth ferrite layer, this is what we obtain. So here I'm plotting the energy density. So I divide by the volume, which is why you see in the non-polar case a line, because the internal energy scales with the volume, as it's only the internal energy. And for the polar case, you see that the energy decreases as a function of the thickness, meaning that for large thicknesses, this is more favorable. And this is intuitively correct, because you imagine that if you create a very large system, you will want to recover the bulk behavior, so find again the ground state. But interestingly, at smaller thicknesses, the non-polar case is more favorable than this extra electrostatic cost. And this explains actually why this non-polar phase is observed experimentally. And I'll just conclude with this. So an interesting property of this, or the initial motivation, was to create antiferroelectrics from a ferroelectric material. And what I'm showing here is the hysteresis loop that was experimentally measured for the system, and is maybe not so clear, but it's actually characteristic from an antiferroelectric material. And it's then a good way to have this antiferroelectric material not based on lead and having an interesting energy storage. So the question I asked initially was, can we stabilize metastable phases controlling the electrostatic? Meaning, can we go to a phase that is not the ground state by controlling what happens at the interface? The answer is yes, it was actually achieved, and we identified this non-polar phase that turns out to be actually also antiferroelectric, which is interesting for application. So that way shows a promising new design strategy in order to build other antiferroelectric materials or find different properties by not only controlling strain, which is always done, but by also controlling the electrostatic at the interface. And with that, I'd like to thank you with your attention. And if you're interested in what I talked lately, you can find a first version of it on the archive at this link. So thank you very much.
Muchas gracias por la presentación, muy interesante. Mi pregunta está asociada un poco a las propiedades magnéticas. Digamos que tiene dos tipos de estrella, uno generado por el sustrato y el otro tal vez por el espesor del, en este caso, la película. Tal vez en términos de las propiedades magnéticas, ¿qué propiedades tienen?
¿Puedo contestar en inglés? So we studied also, because I guess your idea is it different than G-type? Could be a different magnetic order, and could there be something interesting at the interface? So from a theory point of view, according to symmetries and what could be allowed by symmetry, we didn't find that there is a different magnetic order, and from DFT it doesn't show that neither. An interesting thing that could happen is maybe the motivation of your question is magnetoelectricity. So the coupling between the field and the magnetic moment, and that's what we studied by symmetry, and we didn't find that it could be allowed to have something different. I mean, a linear order is not allowed by symmetry for this structure. And experimentally, there were measurements, but they are still doing some measurements. So it could be that there is something, but I don't have an answer of what is happening yet. Yeah. Yeah, sorry. So here in light blue, you are seeing the current. And in dark blue, you are seeing the polarization. And where you can see that it's antiferroelectric or going to antiferroelectric is because here is shrinking, so going to a linear behavior. But also you see here two peaks for the current, which show inversion of the current like up and then down. And this is also characteristic.
Could you comment on the specific applications of having an antiferroelectric and an antiferromagnetic? Because I can see in a straightforward way the applications for a ferromagnet that is controlled by electric field or with a ferroelectric. But for an antiferromagnet with an antiferroelectric, how can we use those?
So from a multiferroics point of view, that's not so interesting, I would say. Because as I said before, in general, one look for magnetic, for electric, or at least one of the properties. So that's not what is interesting. And in that case, to have antiferromagnetic and antiferroelectric is interesting only from the antiferroelectric point of view, except if we find that there is an interesting coupling or change in the magnetic order. But let's say on this answer from these results, I would say it's not interesting from a multiferroic point of view, but more from a ferroelectric point of view or antiferroelectric for energy storage. Yeah.
And what other hope can you give us besides the Perovskite for the antiferroic application?
Yeah. You mean generally, not on this?
Yeah, I mean generally in terms of symmetry groups, besides the ones that the Perovskite can form, which other groups, I don't know, could there be some cubic structure that is not Perovskite that can be multiferroic?
Yeah, so there are some materials. I'm not expert on them, so I cannot give you details, but I know that there are some materials that are not with the Perovskite structure. For example, the yttrium manganite or this type of materials that also combine this ferroelectricity and magnetism, and they are not with the Perovskite structure. And I think that there are also some studies that use more molecules in order to build these multiferroics. But I cannot give you more details, sorry.
Has this been synthesized in some single crystal form, or this is just a strain effect, like having this new phase?
Yeah.
This is just a matter of the strain effect between substrate and...
So you mean that case here?
Yes.
So it has been tried, different heterostructures on the same strain, which I don't show here, but I'll talk about it tomorrow. So what they tried is to change, instead of the lanthanum bismuth ferrite, first you can change the concentration of lanthanum. When you increase the lanthanum, you go to more non-polar, or you change the dielectric constant of your material. So you change the screening, still on the same substrate. And what they observed is that doing that, you see coexistence of antiferroelectric and ferroelectric phase. And you can also change the material surrounding on the same substrates always. And they tried with strontium titanate, which has a large dielectric constant, meaning a low energy cost to screen. And in that case, it stays ferroelectric, polar, in the whole film. Which is why also we think that its strain is one of the ingredients, but the main one is the electrostatic. Because controlling electrostatic, you can change with the behavior. So, yeah. But let's say for different application, out of bismuth ferrite, to try this same strategy, there are different ingredients that should match. And I think they're maybe not so easy to find, because the first one should be that you should find a phase that is not too high energy above the ground state. Otherwise, the electrostatic would be lower than this. And that's maybe one big ingredient that is important to find. And probably bismuth ferrite is one of the easiest to distort structure. But yeah.